Okay, let's take a couple minutes to talk about states of matter. And I know this is something that you've all known since you were probably 7 or 8 years old. So we'll go through this fairly quickly, but I did want to take a few minutes to talk about states of matter from the perspective of macroscopic and microscopic representations that we were talking about last time. All right, so as I think you probably all know, the physical states of matter are solid, liquid, gas, and plasmas. We'll talk about plasmas a little bit here, although there's something we don't, I would say we don't encounter them very often, but actually you'd be surprised how many things around you see are plasmas. We'll look at that in a few minutes. Okay, so in order to understand the different states of matter and why one state may predominate over another, we need to look at intramolecular and intermolecular forces. Now, intra is a prefix that means within or inside, and inter means between, right? So intramolecular forces are the forces within the molecule, and the intermolecular forces are the ones between molecules. We can see what this means if we look at something like water, right? And water, as we saw before, has an oxygen atom, and it's connected, that oxygen atom is connected to two hydrogen atoms. Okay? Now, the intramolecular forces are these bonds right here that hold the molecule together, the bonds between the oxygen and the hydrogen. Those are our intramolecular forces. Okay? The intermolecular forces are the attractive forces between two neighboring molecules. And everything, whether it's a solid, liquid, or gas, everything has some intermolecular forces operating. They might be very strong, they might be very weak, they might be in between, but there's always some intermolecular force which is trying to pull those particles together. All right, we'll look and see how that impacts the states on the next slide, or a couple slides. Intermolecular forces. All right. Okay, so let's look at solid to start with, right? The simple definition of a solid is it's something that retains both the volume and the shape. So if you have a hunk of iron, right, and then you put it in a beaker, it's still going to have the same size and shape, right? It's not going to change based on what you put it in. So the reason for that, if we look at the microscopic representation, and this might be kind of hard to see on your computer because it's a kind of a small picture here, but we've got all these water molecules here, and in between them all, there are these tiny little attractive forces operating between each of the individual molecules, right? And those forces between the individual molecules, of course, as we said last time, those intermolecular forces lock all of the molecules in place so that none of the molecules can move relative to one another. All of these molecules are vibrating, right? But they can't rotate and they can't move from place to place. They're locked in position. And because they're locked in position, the bulk material, the ice, can't change its shape, because in order to change shape, the molecules would have to move around. Okay. All right. Compare that to liquid. And liquids are those things for which the volume is constant, but it assumes the shape of its container. So if we had some water and we put it in a beaker, water would look like that. And if we took the same water and put it in an Erlenmeyer flask, then it would look like that, right? So the shape changes depending on the vessel, but the volume of those two liquids is equal. Well, it's the same liquid transferred to two different vessels, right? So the volume stays the same regardless of the vessel. So we can look at this also. That's the macroscopic definition of a liquid. We can look at what's happening on the microscopic level. And what's happening here is there are still intermolecular forces that are holding all of the water molecules in contact with one another, but the forces are no longer strong enough to keep them locked into place. So they're still sticking to each other, but they're not locked into place. Right? And that happens because of greater thermal energy, right? As you increase the temperature, the molecules start moving around faster, and when they move around more, they essentially kind of break those intermolecular attractions, or maybe we could say the intermolecular attractions are no longer strong enough to hold them in place, right? It's like taking a bunch of second graders, telling them to sit in their desks and then giving them a bunch of coffee, right? You're just not going to be able to make them stay into place, right? Okay. And then the last one is gases. And gases, of course, are those things for which both the volume and the shape are of the gas are those of the container. So if we had a liquid, we put it a round container like that, we'd have to put a little stopper in there, right? And the gas would fill up that container, right? And if we had put it in some kind of a cylinder like that, the gas would fill up that container, right? Doesn't matter how big the cylinder is, doesn't matter what the shape is, it's going to fill up the entire volume that's available. Okay. But you guys know that already, right? So if we look at the microscopic representation for the gas, what's happening here is you put more thermal energy in, the molecules are all moving around so much that the kinetic energy of the motion of the molecules overcomes those intermolecular forces to such an extent that not only are they not locked in place, but they're now no longer held in contact with each other. And all of the molecules can kind of fly off in whatever direction they want to. This little drawing here is not really to scale. Typically, the molecules in gases usually are a lot further apart than they appear to be in this drawing here. So again, it's the idea of the kinetic energy, the thermal energy, overcoming the power of those intermolecular forces that are trying to hold them together. All right, now let's look at plasmas. And plasmas you may not have talked about very much. They sound very exotic, but they're actually pretty common once you know what they are and what to look for. And some of the plasmas that you may be familiar with are lightning and the northern lights, which you can't usually see in Virginia, but hopefully some of you have seen that. I've never seen it. I really want to go see it. It's one of the things on my bucket list. But anyway, lightning, the northern lights, the surface of the sun is a plasma. Inside of these new compact fluorescent light bulbs is a plasma. And in fact, I don't have a picture of it here, but neon lights are the same way. Neon lights is just a long evacuated tube, and that's usually curved into the shape of letters or whatever. But you have a high voltage across that, and it causes a plasma to form inside that tube. Right? Same thing is going on here. And plasmas also include plasma TVs. And a plasma TV, you can't see them because they're really, really, really small, but each pixel on the TV contains 3 tiny cells, a red cell, a blue cell, and a green cell, and each one of those cells can be excited to contain a plasma. And then the plasma causes the cell or the pixel to glow either red, blue, or green. And of course, plasmas also include lightsabers, right? We don't really know what lightsabers are because we've never had one or studied one, but a lot of people have postulated that if a lightsaber did exist, it would be some kind of a plasma. All right, so what is a plasma? You've seen what they look like. Plasmas are like gases in that they occupy, or they expand to occupy the shape and the volume of their container. So they're like a gas in that sense. They're unlike a gas in that plasmas can conduct electricity, and plasmas are also influenced by electric and magnetic fields. There's an important example of this plasma and electric and magnetic fields. This will come up in a chapter down the road. We'll talk about structure of the atom and subatomic particles. But the Thomson cathode ray experiment, this was in about 1897. All right. And this, again, this is really exactly the same thing as a neon light. Right? This right here is an evacuated tube, and there are some wire connectors here that are hooking that up to a powerful battery, and you get a very large voltage across this. You get a negative voltage here and a positive voltage here, and when you do that, you get this kind of a glowing beam in the middle of that tube, right? And that glowing beam is called a cathode ray. And what Thomson did is he was playing around with this cathode ray, and he found that if you put a magnet next to the beam, you could cause it to change directions, right? You could bend the path of that beam. So this is a picture of someone holding a magnet next to a cathode ray. You can do the same thing with electrical fields, and Thomson used this kind of experiment, changing the strength of the electric field and measuring how much the ray deflected, and that was how he proved the existence of electrons. Right? We won't worry about that for right now. I just wanted to show you an example of a plasma, and in particular an example of how plasmas are impacted by magnetic fields. Right? If you go into like Spencer's or one of those places where they have those little plasma balls, you can stick your hand on it and the little beams go to your fingers and stuff. If you have a tiny little magnet, you can move the magnet around that globe, and you'll see the beams being moved by being near that magnet. Okay, so on microscopic level, what is a plasma? A plasma is a substance that has absorbed so much energy that it doesn't just break down the, I keep saying break down, that's maybe not the right word. The energy doesn't just overcome the intermolecular forces that hold the molecules near one another, but the energy of the molecule becomes so large that it overcomes the intramolecular forces that hold the molecule together, and even the forces that hold the atom together. So it absorbs so much energy that it just basically breaks up into little tiny fragments. And this drawing is too small to see very well, but what this drawing is indicating is that what you're left with are atoms with slight positive charges and some electrons that get ripped off. The atoms just absorb so much energy that the electrons, not all of the electrons, but a few electrons are ripped out of the electron shell, and so you're left with charged ions, right? The atoms become ions, and you've got a whole bunch of electrons moving around. And this is why the plasmas can conduct electricity, because they're full of positive and negative charges. And this is also why they're influenced by magnetic and electric fields. All right, so the important thing to understand here in terms of states of matter, like I said, you all have been familiar with solids, liquids, and gases, maybe plasmas, since elementary school. But the important thing that I want to get here is that the state of matter depends on those intermolecular forces, right, which lock all of the molecules in place. And then as the material absorbs more energy, absorbs more thermal energy, right, and the temperature increases, temperature goes up, that adds more kinetic energy, the molecules all start moving around, and eventually they get enough kinetic energy to overcome the intermolecular forces, and they're no longer held rigidly in place, and the molecules can start to move around a little bit, and that's when it goes from being a solid to a liquid. If it absorbs even more thermal energy, then the molecules overcome the intermolecular forces to such an extent that they're no longer held in contact with each other, and they can fly off independently, and that's when the substance becomes a gas. And ultimately, if it absorbs enough energy, then you can overcome the intramolecular forces. Boy, I apologize for the handwriting right here. I will do better in the future. I'm just doing that. I'm going ahead because I know that you know what the word is, but that's intramolecular forces, right? If it absorbs enough energy, then it can overcome the intramolecular forces that hold the atoms and molecules together, and the atoms and molecules then just break up into their components, and you get ions and electrons, and that is what gives you a plasma. All right, so to summarize, 4 states of matter: solid, liquid, gas, and plasma. I'm sure you're already familiar with that. The bulk properties, we've been talking about states of matter, but this is also true for things like boiling point and vapor pressure and viscosity and some other properties we may talk about down the road. Most of those bulk properties depend on the intermolecular forces, which are the forces that hold the molecules in contact with one another, right? The forces between the molecules. And changes in state, going from solid to liquid to gas to plasma, are the result of a competition between the attractive forces, intermolecular forces in most cases, and the kinetic thermal energy of the particles. As they move around more, they begin to overcome the forces that hold them together, and they move apart from one another. Right? And in the case of plasma, they absorb enough energy that the molecules and atoms themselves begin to break apart. All right, wonderful. All right, that's it for states of matter. Thank you all for listening, and I look forward to talking with you again.